Here is the flat plane, and here is a small tile sitting in the corner. The unit square, one across and one up, with area exactly 1. Now hand that square to a matrix. The matrix is a machine that stretches and shears the whole plane, and the square goes with it. It slides into a parallelogram. And here is the one question that matters. By what factor did the area change? That single number attached to the matrix is called its determinant. Everything today is about reading it. So what is that number really? Read the two columns of the matrix as two arrows leaving the origin. They frame a parallelogram, and the determinant is its area. I said signed area, and the sign is not a detail. It is orientation. If the arrows keep their usual counterclockwise order, the determinant is positive. Flip them past each other, and the sheet turns over. The determinant goes negative. The size tells you the stretch. The sign tells you whether space was flipped like a mirror. 2. And the area doubled. 1. And it is untouched. And 0. Hold that thought. It is the most important value of all. The same idea climbs into 3 dimensions without a single change. Here are the 3 axes. And this time our tile is the unit cube. 1 by 1 by 1 with volume 1. Hand the cube to a 3 by 3 matrix and it slides into a slanted box, a parallelepiped. Now the determinant is the factor by which the volume changed. This matrix doubled every side. So the box holds 8 of the original cubes. And its determinant is exactly 8. 2 along each axis, 2 cubed, 8. The picture and the number agree. Now the value that matters most. Take the unit cube again. But this time, a matrix that squashes the third direction completely flat. Watch what happens. The cube is pressed down until it is a flat sheet, with no thickness at all. Its volume is now 0, and so is the determinant. A 0 determinant is the alarm bell of linear algebra. It means the transformation crushed space into something lower, a volume into a plane into a line. Information is lost, and it cannot be undone. So this one number carries a lot. Non-zero, and the matrix is invertible. Space is merely reshaped and can be undone. 0, and the matrix is singular. Its columns are dependent, and there is no way back. And a 0 determinant unlocks a whole chain of equivalent facts. It means the columns are linearly dependent. It means space collapses to a lower dimension. And it means 0 is an eigenvalue of the matrix. Some non-zero arrow gets sent straight to the origin. These are 4 ways of saying the very same thing. Enough pictures. Let's compute. For a 2 by 2 matrix, the rule is beautifully short. Multiply the main diagonal, a times d. Multiply the other diagonal, b times c. Subtract main diagonal product minus off diagonal product, AD minus BC. That is the whole formula, and it is worth knowing cold. One quick number. 2 times 4 is 8, 3 times 1 is 3, and 8 minus 3 is 5. The determinant is 5. So this matrix multiplies areas by 5. 3 by 3 takes a little more care, but it rests on the 2 by 2 you just learned. The trick is called cofactor expansion, and we'll walk along the top row. Every position carries a sign, laid out like a chessboard. Plus, minus, plus across the top, and it alternates from there. The rule is -1 to the power row plus column, but the checkerboard is easier to remember. Start with the first entry. A cross out A's whole row and A's whole column, and a smaller to by to survives. The 4 corners that are left. Its determinant is called the minor of A. Do that for all 3 entries of the top row, attach the checkerboard signs, and here's the full expansion. A times its minor, minus B times its minor, plus C times its minor. Notice the middle sign is a minus. That is the checkerboard doing its job, and forgetting it is the single most common mistake. One freedom though, You may expand along any row or column you like. Pick the one with the most zeros, and the work melts away. Let's expand a real one, top to bottom, hiding nothing. Here is and we'll run the cofactor expansion along its first row. 2, 1, 1. First term, 2, times the minor you get by deleting its row and column. The 2 by 2, 3, 2, 1, 2. That determinant is 6 minus 2, 4. So the first term is 2 times 4, 8. Second term, and mind the sign. It is a minus. 1 times the minor 1, 2, 0, 2, whose determinant is to minus 0, 2. So this term is minus 1 times 2, minus 2. Third term, sign back to plus. 1 times the minor 1, 3, 0, 1, whose determinant is 1 minus 0, 1. That term is plus 1. Now just add the 3, 8, minus 2, plus 1. 8 minus 2 is 6, plus 1 is 7. The determinant of A is 7. A handful of properties turn ugly determinants into easy ones. The star is the product rule. The determinant of a product is the product of the determinants. Multiply the matrices or multiply their determinants, same answer. Transpose a matrix, flip it across its diagonal, and the determinant does not budge. Rows and columns are on equal footing here. Scale the whole matrix by a number c, and the determinant scales by c to the power n, where n is the size. Every one of the n rows got multiplied, so the factor compounds. This one trips people constantly. And the gift of the whole subject. If a matrix is triangular, all zeros on one side of the diagonal, its determinant is simply the product of the diagonal entries. No expansion, no work. And the product rule quietly pays to dividends. At times, its inverse is the identity, whose determinant is 1. So the determinant of the inverse must be 1 over the determinant of A. They are reciprocals, which also confirms why a singular matrix with determinant 0 can have no inverse at all. And multiply a matrix by itself k times, and its determinant is simply raised to the k. Powers of the matrix become powers of a single number. One more set worth memorizing: how row operations move the determinant. Swap to rows and it flips sign. Scale a row by k and the determinant scales by k. But add a multiple of one row to another, and the determinant does not change at all, which is exactly why that move is safe for creating zeros. Watch the triangular shortcut pay off. This has nothing but zeros below its diagonal. It is upper triangular. So we skip cofactors entirely. Just multiply the diagonal. 1 times 1 times 2. The determinant is 2. That is the entire calculation. Now suppose we double the whole matrix. Do not just double the determinant. It is 3 by 3. So the rule says 2 cubed times the determinant, 8 times 2, 16. 3 rows each pulled in a factor of 2, and 8 is the price. Your turn. Here is a fresh 3 by 3. Before I solve it, pause the video and try it yourself. And here is a nudge. Look for the row or column with the most zeros and expand along that one. I'll wait. Here is the clean route. The middle column is 0, 0, 1. So 2 of the 3 terms vanish before you start. Only the bottom entry, 1, contributes. Its position is row 3, column 2. So the sign is minus 1 to the 5th, a minus. The surviving minor is 3, 2, 2, minus 2, whose determinant is minus 6 minus 4, minus 10. Minus 1 times minus 10 is 10. The determinant is 10. If you got that, you've got this. Trap 1. The product rule is seductive and people extend it to sums. Do not. The determinant of a sum is not the sum of the determinants. There is no simple rule for a plus b at all. Trap 2. Scaling. Pulling a constant out of a determinant costs c to the power n, not just c. The bare c only works for a 1 by 1. For anything bigger, the exponent bites. Trap 3. A zero determinant does not require a row of zeros. Any linear dependence does it. Take 1, 2 on top and 2, 4 below. The second row is just twice the first, and the determinant is 4 minus 4, 0. Let's lock it in. The determinant is one number that tells you the area or volume scaling of a matrix, with a sign that flags whether space was flipped. 2 by 2, it's AD minus BC. 3 by 3, cofactor expansion with the checkerboard signs. And for triangular matrices, just the product of the diagonal, and the value to watch is 0. 0 determinant means singular. Space collapsed, columns dependent, no inverse. Non-zero means invertible and fully reversible. Read that one number, and you already know the matrix's character.